And today, coming to the lecture, that yesterday you had a very exhaustive lecture on radiative transfer process. Actually, when we talk of transfer process, there are three types of transfer process. One is radiative transfer, another is convective transfer, and third one is conductive transfer. In fact, anything transferred within the soil is coming under conductive transfer. In the microclimates, these two things, radiative and convective, are important. So, I don't have much time to cover this conductive part. I'll stick to the convective transfer process. And coming to my lecture, let me share my screen. Can I share my screen now? So it will be just 1 second. Now, I think you can see my screen here. Now, can you see it? So, when you are considering convective heat transfer, there is a little bit of more complexity associated with convective heat transfer, because when we are talking of radiative heat transfer, it is simple geometric in nature. I mean to say, atmosphere has just one role: its optical density, how much it will restrict to come. Otherwise, the other things are mainly geometric: angle of incidence, angle of reflectance, absorption, then energy balance, radiation balance. These are very important aspects, but mathematical computational complexity is comparatively less. But when we are talking of convective transfer, there is actually the convective heat transfer uh, involves some kind of boundary layer. Boundary layer means the air layer, in this case, atmospheric layer between the source and sink. Say, for example, plant is the source or canopy is the source, and sink is the atmosphere. So atmospheric motion is coming to play here, because it is related to the molecular level transfer, means the molecules carry the heat and move. So naturally, this atmospheric stability is important here. Atmospheric turbulence is important here. Laminar or turbulent boundary layer concept is important here. Now, when all these fluid dynamics concepts come, that makes the whole computations a bit complicated. I'm sorry if I am going to give more number of mathematical equations, but I request you, please do not think about much about the equations. Let us understand the concept. Yes, the equations will come. I'll try to make things easy for you. But first, let us define what a boundary layer is. Now, where we meteorologists stand? See, we know about the atmospheric boundary layer. That is, you can say, total atmosphere. If you put it in different layers, it will be troposphere, stratosphere, mesosphere, thermosphere. These are simple things you know in your geography. Now, we micrometeorology stands within a small part of the troposphere, lower part of the troposphere, and within this troposphere, we are having a rough layer. Surface, top surface is exposed to the atmosphere. Then after that, you are getting a fluid surface layer where the fluid sphere dominates. Then you are getting a vertical mixing layer. Then after that, there is free atmosphere. When I'm saying free atmosphere, means this layer at which there is no influence of surface friction. So the whole thing is defined as planetary boundary layer. So planetary boundary layer domain starts from surface to the pre-atmospheric layer up to this curved line. This is my planetary boundary layer. And this is the, you can say, lower part of the troposphere, which is influenced by surface lying, underlying surfaces. So the surface layer is there in the bottom, and this surface layer is offering some kind of heat exchange, mass exchange. All these things are influencing the boundary layer itself. So this is what we call a planetary boundary layer. Now the thing is that what is the depth of this planetary boundary layer and how the characteristics of this planetary and boundary layer can be defined. So basically, the planetary boundary layer is characterized by rapid fluctuation of temperature, humidity, wind velocity, and concentration of different gases. So all these factors, all these constituents plus wind plus temperature, these things are mixed up here. There is a rigorous, strong vertical mixing among these layers. However, the general trend is there. The general trend divides this planetary boundary into different subcomponents. And above the planetary boundary layer, there is free atmosphere. So free atmosphere is not influenced by surface as I told earlier. Now let us come a bit details into it. So this planetary boundary layer structure is dynamic. It is not fixed for the whole year, fixed for the whole day. No, its depth is changing with time. Its depth is changing with season. Its depth changes with eternally. So now let us see it. This is my surface, rough surface. Now during daytime there is heating, terrestrial radiation. Heating due to terrestrial radiation, the atmosphere becomes unstable and the convective boundary layer sets to develop. See this layer. This is my target layer, this middle one. Now here there is heating and this target layer is increased in depth. Now in the second part, during night, there is radiational cooling, there is downward flux, and that brings the layer, squeezed it backward. So this becomes a nocturnal boundary layer. So these dynamics takes place over the year throughout the day. So these dynamics takes place as there is a heating balance. So now, however, from general trend, if you see, the lower part of the surface, this PBL is called surface layer, which is about 10% of the PBL. The middle core part is called PBL core, that is 10% to 70% of the PBL depth. And the upper part, that is a entrainment zone, that is a transition between pre-atmosphere and PBL. That part is around upper 30% of. So this is how the PBL is basically divided into three basic components. Now the depth of PBL depends on several factors like pre-atmospheric wind. Suppose pre-atmospheric wind speed is high, that means the PBL depth will decrease because pre-atmospheric wind speed influences more up to deeper layer. And when the surface heat transfer is more, the PBL is stressed upward. When there is density stratification, it has its influence on PBL. I'll talk about density stratification specifically in my subsequent slides. So now I am not telling about the density stratification. Then pre-atmosphere wind shear. Let me tell you wind shear. Wind shear means change in wind. Wind means change in wind speed and change in wind direction. So what happens at the surface? There is a wind between high pressure to low pressure. So there is a wind across the pressure gradient or across the isobars. But when it is going upward, if you are measuring wind at the upper level, the wind direction also changes because of the Coriolis force. Sorry. So that Coriolis force changes the wind direction, and it as it is going to the upper part of the PBL towards the end of PBL at the free flow layer, the direction is 90-degree changed. Means there you are getting geostrophic wind. Means that geostrophic wind 90-degree change means that wind is along the isobar, not across the isobar. At the surface it is across the isobar. At the top of the PBL in the free flow zone, it is along the isobar. So this is how the wind shear is there. Shear means change. Now coming to the studying of However, if anyone,
సార్ మీరు
hello.
ఉండగా నేను ఏంటి సార్?
So if you have anything to say, please tell me. I'll break and explain. I don't have any problem. So now there is we are dealing with the PBL. There is convective transfer of heat, momentum, mass, and vapor. Momentum transfer, I'll talk in specials with some specific details. Actually, when I'm saying heat transfer, I mean to say sensible heat flux. When I'm saying vapor transfer, I mean to say latent heat flux. When I'm saying mass transfer, I mean to say carbon dioxide, methane, and all these things. Now, you might be asking me why vapor is not a mass. Yes, vapor is a mass, but there is a point to it. Like vapor transfer involves latent heat. So when latent is involved, then the transfer process can be made simple if you consider it from energy balance perspective. So we'll discuss that part. That's why vapor transfer is kept separately. Otherwise, all other mass transfer, they are put under the mass transfers. Now these three types of transfer system we are considering, and these three types of transfer system has to pass through the PBL, or the PBL is itself the sink and the medium also. So in that case, the characteristics of PBL is important to define the sink strength, and maybe if you think of your photosynthesis, carbon dioxide flux is downward. In that case, PBL is your source and the surface is your sink. If you think of respiration, the reverse is the flow. Otherwise, water is also similar, just evaporation and condensation. Anyway, the flow is from up to bottom or bottom to top, but it has to pass through this PBL. So this PBL characteristics is important, and to know the PBL characteristics, let us understand the PBL a bit more. Like, let us think of a crop or crop canopy in the PBL. So the lower part is soil. This doesn't look like a canopy, but I have put it deliberately in this way to give you a feel of this resistance. Lower part is soil. The middle part, this one is your crop canopy, and above that is your air layer. So when you are considering soil, then the root zone characteristic is important and soil water potential is important. So here this hydraulic conductivity of soil water potential, these are playing a role. I'm talking of water transfer, for example. Then when I'm talking about canopy, the stomatal resistance is important and canopy distribution is important also. And plant water potential is also important for moisture. Then when I'm talking of aerodynamic resistance, I do not have to take all these measurements. I'll have to see only moisture concentration here, humidity at this point, specific humidity and specific humidity at this point. So this makes the concentration gradient. So if you ask soil scientists to find the water loss from by the crop, water uptake by the crop, we can get the soil water balance. That soil water balance will tell us how much water is lost. But soil water balance, it's not a very fast responding process. You have to get the soil water balance for a season or maybe for 7 days or maybe for 1 month. But at hourly scale or at minute scale or second scale, you cannot get the soil water balance if measurement is having certain constraints. And when you are talking of canopy resistance, see, the major problem here is the representativeness. Suppose you are taking the stomatal characteristics. You can take a bottom leaf, it has a different stomatal characteristics. You can take a top leaf, it has a different stomatal characteristics. So transpiration rate differs within the canopy. So now it is difficult to get the overall water loss from the canopy. But at this point, when you are considering it from micrometeorological point of view, you have to only get the concentration here and concentration here. Forget what is there beneath, but you can get from the concentration difference. If you know the aerodynamic resistance, you can compute this vapor exchange. Similar for carbon and similar for all other masses also. Now, let us understand how this boundary layer develops. So, the basic process in boundary development is horizontal flow velocity, and that is going over a rough layer, maybe a curved surface, maybe a rigid rough surface, but it's a rough layer at all. And this layer experiences some force. This surface experiences some force by this wind. So that force is causing turbulence and causing the formation of your boundary layer. Now, if we resolve it this way, this force is equal to how much is the force? Density of air, velocity square, then surface area exposed. When I'm saying surface area, I'm dealing with solid surface, stem surface, all over the integrated surface area. And this Cm is my transfer coefficient. We call it drag coefficient because the force is transferred, then this is drag coefficient. Now, if we consider it from an ideal layer, from a surface layer, rough layer, from the leading edge, this part is laminar, and as you are going certain length of edge, then you are getting a transition zone. After that, the layer is split into two. One is turbulent layer and one is laminar. And there is a viscous, there is a buffer zone in this. Now, I told you two terms. One is turbulent layer, one is laminar layer. I'll have to discuss that. I'll discuss it. Now, this viscous layer is the laminar layer, and the buffer zone is between the viscous layer and the surface layer. Actually, let me tell you the basic concept of laminar layer. Before that, let me finish this slide. Okay. So horizontally from the leading edge, you are getting three zones, and vertically from the bottom, you are getting three zones. One is laminar sublayer, then there is a viscous sub, then there is a transition zone, then there is some kind of turbulent layer, and after that there is maybe free flow zone. So this is how the boundary layer is developed over the surface. Now let us start with laminar flow. Actually, the difference between laminar layer and turbulent layer is the eddies form. In turbulent layer, there are eddies form. Eddies means swirling motion of air particles or whatever media particle is there. It may be water, maybe also turbulent. So, this whirling motion means rotatory motion. Some kind of whirling motion are there in eddies, but in laminar flow, the layers are not broken. The layers are parallel, just one layer over the other without breaking the layer. So, in a very simple way, if you put a drop of ink over a laminar flow layer, this ink will not go to the next layer because the exchange process is very limited. These layers are moving over one another without much exchange. So only the velocity field is changing. That near the surface, this is slow. Above the surface, it is faster. And that velocity is linearly changing. I mean to say du by dz is a linear function of height or a linear function of linear function your maximum velocity. That means u by h. UH means u at height h. So u by h is your du by dz. So this is the velocity gradient. Now this velocity gradient is caused because the surface is observing some momentum. The surface is observing some force. So Newton said that this is called shearing stress, means force observed per unit area. So this shearing stress is tau, and this is proportional to the shear. Actually, deformity is caused by the force, so force is proportional to the amount of deformity, and this proportional coefficient is called your coefficient of dynamic viscosity. Actually, what happens when I am talking of fluids, I always prefer to use density term here. everyone does that. In fluid mechanics, usually density term is used because mass is there over an volume, and the volume is expandable. So unit mass, as because the pressure is not fixed, so the volume is expandable. So it is better to give it to a standard term, that is density. So all these terms are usually expressed in form of density. So this mu is transformed to density into nu. Nu is your kinematic viscosity. So kinematic viscosity is equal to mu by rho. Okay. So this is how the laminar flow behaves. Now, before going into the turbulent flow, we must know when the flow becomes turbulent. So there is certain threshold limit. When that threshold limit exists, then the flow becomes turbulent. That threshold limit is defined by the Reynolds number. So what is Reynolds number? Reynolds number is actually, before defining Reynolds number, you must understand there are three terms associated with heavy flow. One is inertia term, second is friction term, third is the secondary term. Inertia means reluctance to change, reluctance to move. So if it is rest, then inertia of rest. If it is in motion, then inertia of motion. So inertia is proportional to density always. It is density into wind speed by change in wind speed. So you can integrate it to get rho u square by L. L is actually distance from the leading edge. So you may set characteristic length. Now, in frictional term, it is friction is your rho into nu into u by L square. U is your wind velocity. So when you take the ratio of inertia term and frictional term, then you are getting some kind of Reynolds number. You are getting a number that is Reynolds number. That Reynolds number actually defines the characteristics of the flow. So Reynolds number is the ratio of inertia term and friction term. Now obviously the friction term, if you take the friction term, then mu in place of mu should write rho u. So rho will be cancelled in the ratio, and u square and u, it will be u only, and the formula is something like u L by mu. U is your wind speed, L is your length from the edge length or length from the edge of the surface, then mu is your coefficient of kinematic viscosity, that is the characteristics of the liquids. So Reynolds number is a non-dimensional term, and Reynolds number actually defines the characteristics of boundary layer. And let us see how. When two systems are dynamically similar, there should be same Reynolds number. And Reynolds number indicates whether the inertia force dominates or viscous force dominates. When inertia force dominates, then naturally the turbulence becomes imminent, and when viscous force dominates, turbulent is less. For example, see, water is less viscous than oil. If you are having oil flow, you will find very less turbulence in oil flow because the viscous force is more. But in water flow, there is more turbulence because the inertial force is more, viscous force is comparatively less. So that is the situation. Now, usually the threshold limit is 3 lakh to 5 lakh. As Reynolds number exceeds 5 lakh, it becomes totally turbulent. If Reynolds number is below 3 lakh, then it becomes laminar. See, this is for the open atmosphere, the on a plate. If you apply it to a pipe, then the value may be around 2000 or 20,000 within that. So for us, it is important to take it for the open atmosphere where there is a surface only and the open atmosphere outside. So it's not a pipeline condition. So in this case, 3 lakh to 5 lakh is my threshold. Between 3 lakh to 5 lakhs, there is a transition. Actually, there is a mixed layer, a mixed flow. So Reynolds number actually defines the boundary layer condition. Like in this case, the same thing I have told you, I have shown you earlier, the same figure, this figure will come again and again because this figure defines crop in terms of boundary layer. So this is my laminar layer. So here the depth of the laminar layer is defined by the Reynolds number as 5L by root over Reynolds number. So this is the depth of my laminar layer. And this is my turbulent layer here. And the turbulent layer depth is 0.37 L by fifth root of Reynolds number. So these are the two threshold limits of turbulent depth and laminar depth. Now you understand how much should be the depth. Now within this depth we'll consider. Now let us see the characteristics of wind in the uh, turbulent layer actually. Now I left the laminar layer there itself. Now I'm discussing about the turbulent layer. In turbulent layer actually eddies are found. So if you see the wind speeds there is a logarithmic wind profile over the rough surface. So that logarithmic wind profile is defined as uh, UZ means wind speed at height z is equal to A into ln z, logarithm of z, the natural log of z, and then plus b. B is another constant, A is a constant, B is a constant. Now let us imagine a height z0 at which wind speed is 0. It is not the surface exactly, maybe at some height above the surface. So let us imagine something z0 where the wind speed is 0. Now in that case, U will become 0, A ln Z0 and B A ln Z0. B is A ln Z0 is actually equal to B. B will come to the other side. So B is your A ln Z0. Now using these values, we can simply find the wind profile equation, and this is the situation of wind profile. At the surface, there is smaller eddies near the ground. As you are going upward, higher eddies are there, larger eddies are there. Then at surface Z equal to Z0, there is no eddy. So the layer is laminar. So below Z0, the layer is laminar. Now, if it is a vegetation surface, it makes certain difference, certain change. What is that change? Because in a vegetation surface, wind happens to penetrate into the canopy. So it is not Z0 only, there is another factor, how much is the penetration, that is defined by the zero plane displacement. So in place of ln z, I am putting just ln z minus d. So wind is not a function of z only. Wind is a function of z minus d, that is your displacement height. Means some height is imagined over the surface, that is d. Now from that height the wind profile equation starts. So that height is called zero plane displacement. Z0 is the imaginary level at which there is an actual level. We just imagine it this way. Is the level at which wind speed is assumed to be zero, that is called roughness length. And zero plane displacement is d, that displacement height with which wind is logarithmically related, that is your zero plane displacement. So generally zero plane displacement is 0.7 into plane height, and z minus d is displacement height as I told earlier. So now du by dz is equal to a by z minus d. Previously I was saying it a by z, but for top surface it becomes a by z minus d, as I told that all z will put it z minus d as a top surface. Now next, let us continue with wind profile equation a little bit. I may trouble with more mathematical derivations, but without mathematical derivations, it is not possible to understand the underlying processes. So I am forced to do so. Now drag force. Sir, am I becoming too fast? Can you understand me, or should I be slow? Anyone, please?
Yes, it is good.
Okay. Now, drag force per unit area is shearing stress. Means the stress that causes shear. So, the drag force per unit area is our driving force actually. And as per our normal assumption, this driving force is maybe defined as the amount of momentum the surface is absorbed. So that is causing the absorption of force, means the amount of momentum the surface is absorbed. So you can define it in terms of momentum by area by time. Now, if you put it as area, momentum, time, let us separate the velocity part separately and becomes a air density into velocity square. You can get it because momentum is something by mass into velocity. So if you put it, this will be the dimensional analysis. Now the drag force is actually becoming tau is equal to rho u as delta square. And I'm doing it from dimensional analysis. Yes, it is velocity square as per dimension, but there might be some constant involved. So we do not say it as velocity square as such. We rather use the term frictional velocity here. So tau is equal to rho means density into frictional velocity, that is velocity term. So just imagine what is frictional velocity. It is difficult to get a physical perception of the frictional velocity, but it is imagined like that. Suppose there is an eddy form, so there is a whirling motion. So that tangential velocity of this whirling motion is called frictional velocity. Actually, this is how frictional velocity is imagined. Now, we have now few terms. Tau is your shearing stress. This is equal to density into frictional velocity square. Now, mm, this wind drag on the surface is practically the manifestation of downward transfer of horizontal momentum, as I told earlier. Then shearing stress is equal to constant into momentum shear. See, as I told that shearing stress should be proportional to strain, means if we equalize these two, there should be a constant. So momentum shear is this actual strain here, and shearing stress is the stress here. The constant is a proportionality constant. So we can define it this way: momentum into Km, constant of proportionality into density into wind shear. So if you see the mathematical derivation, it's easy. See, this part is by shearing stress, this is constant of proportionality, this is density, and this is wind profile, change, wind shear, you can say, change in wind speed with respect to height. So this is a basic equation on which the transfer process runs. I mean, momentum is transferred from surface to bottom. Now the thing is that how this momentum transfer is becoming important. For that, in one or two slides, I can tell you why it is becoming important. This Km is going to rho into A by Z minus B. And here, just one more imagination that this A, proportionality constant, is A, is equal to U asterisk by K. So, U asterisk is your frictional velocity and K is your von Karman's constant, that is 0.41, that is universally accepted values. So this becomes a very simple formula for me ultimately. Rho U asterisk square is equal to momentum transfer coefficient into rho into pi K. Now equating these two momentum transfer coefficient becomes simply U asterisk into K into Z minus D. This K into Z minus D is called mixing length in micrometeorology, and U asterisk is called your friction velocity. So friction velocity into mixing length becomes my momentum transfer coefficient. Now, if you compare it with laminar flow, then in laminar flow there is a shearing stress, and shearing stress is proportional to this strain, that is du by dz, and you have got nu into rho into du by dz. For a turbulent force, there is an eddy transfer. It's not diffusive transfer. In laminar flow, it is diffusive transfer. Here it is eddy transfer, and it is analogous to kinematic viscosity. And eddy viscosity it is called eddy viscosity or eddy diffusivity. And the formula is also very similar. If you see tau z is equal to km into rho into du by dz, like your nu into rho into du by dz. Here km is into rho into du by dz. Now, if nu is called coefficient of kinematic viscosity, km is called eddy viscosity. So both are called viscosity, but one is for eddy viscosity, the other is kinematic viscosity. So that is how the terms are used, and the other things I have already told these things, and putting the value of du by dz in tau, what we get? We get rho u asterisk square is equal to km rho u asterisk by km z minus d, and this is what I am getting, momentum transfer coefficients. Okay, so why this transfer coefficient is important? Here comes the concept of Reynolds analogy. Reynolds similarity analogy says all the transfer coefficients are same under neutral condition. That means if you understand one transfer coefficient, the same transfer coefficient is applied to water, the same transfer coefficient is applied to the gas exchange also. So you need to quantify the transfer coefficient for any one of it, and it is easy to quantify from the momentum transfer concept, because here you can put it in terms of force and area. So now let us move further. From here we need to understand the aerodynamic resistance. Actually, wherever there is a flux transfer across the gradient, then Ohm's law is somehow involved in certain form. What is the basic Ohm's law? Basic Ohm's law is potential difference by resistance is your current. The current, just imagine current as flux, and potential difference as concentration difference, and resistance is there. This resistance is called aerodynamic resistance. This is how the general flux equation developed based on these fundamental concepts. Now, if I see potential difference, it is momentum concentration at height z and momentum concentration at surface level. I told that potential difference between layer 1 and layer 2. So at height z, momentum concentration, at surface level momentum concentration. What is the momentum concentration at surface? At surface, I know wind speed is 0, so momentum is 0. Now this part is becoming 0. So it is simply momentum concentration at height z divided by aerodynamic resistance is my momentum flux. So momentum concentration means, when I am saying momentum concentration, it is momentum by volume or mass into velocity by volume. So mass into volume, mass by volume, it becomes density, and this is velocity. This is how momentum concentration rho into u. Then what is momentum flux? Momentum flux is simply F by A, force per unit area, or tau. Tau is the momentum flux. Dimensionally it comes like that. Mass into acceleration by area. Mass into velocity by area into time. So mass into velocity by time is your mass into acceleration by area. So it is becoming force by area, tau. So this is becoming my equation. Tau is equal to rho uz by Ra. From here you can get Ra is equal to rho uz by tau. In rho uz, it is as such there, and tau, we know earlier that tau is equal to rho u square. So this rho will be cancelled, and you are getting uz by u square. So that is my aerodynamic resistance. U square is your tangential velocity of eddies, and u is your mean velocity at certain height z. Now, once you know this aerodynamic resistance, the same formula works for all kinds of fluxes, that you get the concentration difference in vapor between two heights, you get the same aerodynamic resistance. Concentration difference by resistance is your vapor flux. You get the concentration difference in carbon dioxide between surface and some height above, and you divide the resistance, you get the carbon flux. So this is a very generalized formula we are getting from aerodynamic concept of boundary layer. That's why I have given you so many mathematical equations to get a generalized formula for aerodynamic resistance and aerodynamic consequences. Now coming to the application of aerodynamic resistance, this same thing I'm putting here. This is a generalized flux equation. So U * is computed. How U * is computed, that is important. Uz is something you are measuring, taking measurement at the field. Then how U * is computed? U * is computed from this equation, that is a generalized wind profile equation. So U * Uz is equal to U * by K into ln z minus d by z0. So Uz into K, just bring the Uz into this side, or take this ln z minus z0, ln z minus d by z0, and K to the other side. You are getting U * is equal to Uz into K divided by ln z minus d by z0. Uz is your height at which you are measuring. K is your von Karman's constant, that is 0.41. Z is the height. U is your wind speed at height Z. Z is your height. D, if it is a plant top surface, then D is 0.7 of your plant height. And Z0 is actually 0.3 of your plant height. So you can easily compute the U * So by that you can compute heat transfer, vapor transfer, carbon dioxide transfer, GHG transfer. Only the coefficients are different. And as per the Reynolds analogy, I have already told earlier, all these coefficients are same. So if you know this U * by U square, U by U * square, then you can get the coefficients, you can get the flux. But this is a very simple version of flux computation. Why I'm saying simple version? So far I have been discussing about the frictionally driven eddies, as if eddies are driven only by the horizon flow of air. But sometimes what happens, the surface is getting heated. Once the surface is getting heated, then what it does, it causes its own eddies. So that makes the situation a bit complicated. Now, under neutral flux condition, as I told, this is your momentum flux, this is your sensibility flux, this is your latent heat flux. Similarly, for all other gases, and according to similarity hypothesis, similarity analogy of Reynolds, Km is equal to Kh is equal to Kb is equal to Kc. But this is all applied for the neutral condition. Now, here we need to understand another concept, that is what is pre-convection and what is post-convection. See, whenever there is a wind blowing up wind and convection is occurring, that gives me post-convection. Because naturally it should not move upward. It is because the wind only it is carried, so it is called post-convection. But if there is no wind, still there is flow of eddies, there is formation of eddies, and that is going upward, then it is called pre-convection. So in pre-convection, how it occurs? It occurs due to the temperature gradient. In post-convection, it occurs due to horizontal flow of velocity, horizontal flow of air. Now just take an example of a hot egg here and hot egg here. Now in this case, there is no fan. Now around the hot egg, what will happen? The air near the surface is getting heated and it is going upward. When this air is going upward, surrounding air will come here to replace, and there is formation of eddies. There is an upward movement. But here no horizontal velocity is involved. But in this case, you see, there is a horizontal velocity and that causes the eddies to form. Yes, thermal component is there because it is a hot egg, but even if it is a cold egg, the same thing will happen. So here the eddies are like this, and here the eddies are like this. This is my eddies. post convection. So this is something like post convection. Now I can give you just one point here that post convection is usually a faster process. Say for example, when I am in hurry to take my meal, what I used to do, I use some fan so that convective heat transfer will be increased. Otherwise, it will as such cool down, but it will take time due to free convection. So forced convection makes the things faster. Now, forced convection is naturally the major contributor of heat transfer. And the same thing is happening to all other fluxes also because the same eddy is transferring all other fluxes. Now, important is to see the contribution of pre and post convection, and you are mostly facing a mixed type of convection. Now, to know the thermally stratified layer, thermally stratified layer means the layer in which pre-convection contribution is there. To know the thermally stratified layer, you need to get an understanding of the Richardson number. So before going into the Richardson number, let us see in wind profile level how this thermally stratified layer behaves. Like you have got an unstable condition, you have got a stable condition. In stable condition, there is downward trend of flow and air mass tend to move downward. So this is stable. And in unstable condition, air mass tends to move upward. This is more convective. Now, under neutral condition, this is our wind profile. I have shown this figure earlier. But under unstable condition, the wind profile becomes stiffer. So it is something, these eddies are elongated. Then when you are going for the stable condition, these eddies are elongated horizontally. So this becomes, this is how this wind profile changes. Accordingly, the whole equation also changes. So if you put it in logarithmic scale, the neutral will be linear because the relation is logarithmic. So if you put it in log scale, it will show you linear value. The unstable is, we said, upward. The stable is tilted downward. Now, under neutral condition, this is my equation. This is my shearing, wind shear, and under non-neutral condition, there is an additional factor. This is just the additional factor. We call this as stability factor. Now, this stability factor, this is the integrated form, and this is the differentiated form. Sorry, this is the integrated form, this is the differentiated form. Now, to understand this stability factor, we need to understand the Richardson number. So, what is Richardson number? It is just a ratio of turbulent kinetic energy and the buoyancy kinetic energy. So turbulence force and buoyancy force, this ratio defines the Richardson number. So this upper part is actually buoyancy, the lower part is the turbulence. Why it is buoyancy? Because this T, temperature is involved. Temperature is causing this buoyancy force. Now, if you integrate it, the relation is becoming simple. G means gravity divided by average temperature of the layer. Then temperature at height 2 minus temperature at height 1. Then height 2 minus height 1 divided by wind speed at height 2 minus wind speed at height 1 square. Okay. So this makes me Richardson number. Now, how this Richardson number is related to stability? If Richardson number is positive, then the condition is stable or inverse. In micrometeorology, we do not differentiate between stable and inverse. Usually, stable means to consider it as inverse, and neutral means there is no change in. Otherwise, neutral stability is inverse, and stable condition, these are clearly different. But when we say it's stable, means it is mostly inverse condition. Now, in case of unstable condition, Richardson number is negative, and the formula becomes 1 minus 16i whole to the power 3 by 4. In case of neutral condition, F becomes 1. So the equation accordingly changes. Changes means simply you have to multiply this factor with the normal equation. With the neutral equation, you just multiply this stability factor. If it is neutral, then 1 is multiplied, same equation holds good. If it is negative or positive, accordingly different value of F multiplied. So the equation changes. See, this is the simpler version of your thermally stratified layer. If you want to know the details about it, I would suggest you to go for the Monin-Ovikov similarity theory. It gives you very detail of this thermal stratified layer. Today, it is really difficult to explain this whole Monin-Ovikov similarity theory here in this small time period. Actually, micrometeorology is a vast subject. So I'm just trying to get the simpler part of it. Now, uh, this is a graphical presentation of Richardson number and stability. See, this is poorly forced convection, that is neutral stability condition. And this is damping of forced convection, that is as you are going to inversion situation. And this is upward motion is predominating, means there is a free convection zone is there. So from here, no convection, that is highly inverse, to a damped inverse, then to a forced convection zone where the thermal effect is minimal. Then there is a thermal effect increasing, so the free convection zone is gradually coming to free convection zone. So this is how graphically you can represent the Richardson number. Now, so these are the things we just discussed. I'm not going into the exact value of RI and how it plays. So basic concept. Now this makes our job a bit simpler, that if you consider the Richardson number for the thermally stratified boundary layer, then you may come to the final your final approach for the flux computation. That is, one is bond ratio energy balance approach. See, we so far we have discussed about the aerodynamic resistance system, in which we know the concentration difference and the intermediary resistance between these two layers. And in that case, how can you compute flux? Now, coming to the bond ratio energy balance approach, it is a simpler form of flux computation and particularly applicable for the latent heat flux, not for the others. Now, if you see that aerodynamic formula, your H is actually KH means heat transfer coefficient into rho into Cp. Rho into Cp is practically your capacity capacity of heat for the air pocket. Cp is your heat capacity and rho is your density. And theta is your actually you can write it T, but conventionally theta is said when there is a potential temperature. In micrometeorology, there is not much difference between potential temperature and actual temperature, because see, we are considering a smaller layer. Within this smaller layer, the pressure varies little. So potential temperature is almost same as actual temperature. Now d theta by dz, some people write it as dt by dz. There is no harm in it. Now, in this is my general formula for heat transfer. This is my general formula for vapor transfer. This rho Cp by psi, this is exactly we can say the vapor capacity. You can say psi is your actually psychrometric constant. Psychrometric constant actually the value is 0.066 kilopascal per degree centigrade. So this is defining the vapor capacity, or you can say moisture capacity of the air pockets when it is multiplied with E, or vapor concentration when it is multiplied with E. E means vapor pressure. Vapor pressure and vapor concentration relationship is defined by this formula. Now, the Bowen ratio is actually ratio between sensitivity plus and latency plus. Let us assume this ratio as beta. Now, beta is equal to h by L. Now, I can easily write h as b into L. So, this is what I have done. I first compute the beta. Beta, for that computation, you take this ratio of these two, and the ratio of these two, most of things are cancelled because under neutral condition, KH is same as KB, as you know. CP cancelled, rho cancelled, only psi is remaining and delta z cancelled, and you are getting psi into d theta by dt or psi into d t2 minus t1 by e2 minus e1. I told that theta means potential temperature. I can write theta 2 minus theta 1. Instead, I can write T2 minus T1. It doesn't make much difference. Within 2 meters, the pressure doesn't vary too much. So, now from here, I can compute the total Bowen ratio. And once I get the Bowen ratio, if I take the measurement at two levels, the temperature measurement and vapor pressure measurement at two levels, means simply if I can have a psychrometer that is having dry bulb and wet bulb thermometers, and dry bulb will give you temperature and dry bulb wet bulb combination will give you vapor pressure. So if I get the computation and get the measurement of P and E air at 1 meter and 6 meter depth, or at 5 meter and 6 meter depth, this difference will tell me how this Bowen ratio behaves. Now, under neutral condition, KH is equal to KB, so it is easy to cancel these things. And ultimately, the energy balance equation, as you know, maybe yesterday you have studied this thing. H plus L plus G is equal to Rm. So, in place of H, I can write beta into L. So, beta into L plus G, and I can put L is equal to Rn minus G by beta plus 1. So, this is my simple formula to get the flux, but original this formula is derived from the aerodynamic transfer systems. I'm just showing it how it is simplified. So simple things are not bad. Let me tell you, under thermal stratified layer there might be some problem, but under neutral layer this is good because simple things are easy to extrapolate. Say for example, if I know the surface level vapor concentration, if I know the air temperature, air vapor concentration, if I can derive these things from different climate reanalysis, like your ERA file and other things, you can still compute the vapor flux from the ERA file. So you can get the vapor also in ERA file. The most of the spatially expanded models, that is your maybe your Penman Montieth or maybe your Unfed. These are based on energy balance because of its simplicity. So all these energy balance based models are working for estimation of evapotranspiration. So this understanding is important because once you understand the very basic of aerodynamic layer and this boundary layer condition, then you can easily understand the ET estimation different methods. Now, this is an example of Bowen ratio energy balance apparatus that we used a few years back at BCKB. These are the heights of measurement, two heights. When we're having a high-end data logger, we have to get the data at every half-hour interval, and it is sent to the insert server, based server, most stack. So this is a collaborative project with ISRO, and it was first time we developed some kind of tower network for ET estimation at different cropping situations in agriculture. So this is a breakthrough project. I'm happy to be a part of that project. So then computation of flux in eddy covariance approach. This is the last part of my lecture. Probably I'm little bit extending this 9 now. Okay, I'm well in time, I think. So any problem? Anything? Any questions so far? because we are covering one person, other persons, and we are dealing with so many complicated things. There might be some questions. Anyone can ask me anything at this stage before going into the next stage of our study. If I am not getting any questions, let me continue with it. So, eddy covariance approach is little bit measurement wise, it is very complicated. But computation wise, it is not that complicated, or the boundary layer concept is not that way understanding is required. It's not that much understanding is not required. But the measurement wise, it is complicated. So, this is a typical eddy covariance tower. This eddy covariance system has two basic components, two essential components. One is your infrared gas analyzer. The other is your uh, sonic anemometer. When I'm saying infrared gas analyzer, then I'm measuring carbon dioxide concentration, vapor concentration, and air temperature. The three things are simultaneously measured. So it is not only gas analyzer, means it is not only CO2 measurement. It integrates these three things by default. So when I'm talking about sonic anemometer, that measures the wind speed at a very faster rate. So now the measurement system becomes complicated because the principle requires very fast measurement. I can tell you how fast it is. It is around 20 hertz. 20 hertz means within a second you need to take 20 minimum 20 number of measurements. Then only you can get the fluctuations. And once you get this fluctuation at a very minute scale, then only you can compute the eddy. You can compute the flux. So let us see how it works. Actually, it relies on fluctuating component of wind in the surface boundary layer and its association with fluctuations of temperature, humidity, and gas concentration. So usually when you are measuring wind, we are measuring horizontal wind, but eddy covariance system makes three components of wind. One is your vertical component, horizontal X and horizontal Y and Z. So X component, Y component, Z component. For the computation, this Z component is used. So this Z component means vertical wind speed. Now fluctuation in vertical wind speed is used for this purpose. And at a glance, formula is like that. But this is not all. Let me tell you the formula in details. Rho is air density. Your omega is vertical wind speed. And S is your concentration of quantity. This concentration may be heat, vapor, or any other gas. Among this, let us choose heat transfer for this understanding. All of the transfer are following the same process. Now, at a time t1, this is the eddy. This is time t1 eddy. At time t2, this is the eddy. So if you see rotating this way, so these eddies, there is no definite direction of rotation, it is random usually. So when these random eddies are there, if you take the average upward wind, yes, it is there. But if you take the fluctuation, yes, it is there. But if you think that the air pocket is going upward, then how this space is actually filled up. So there is at the same time some downward, upward, both ways there is movement. You may say that there is horizontal motion. No, I'll not accept this horizontal motion because field is very large. So for small eddies, the replacement is not horizontal, the replacement is vertical itself. Now, how it is computed? So in mathematical terms, eddy flux is computed as covariance between instantaneous deviation in vertical wind speed and mean deviation, mean and instantaneous deviation in ground with gas concentration, mixing ratio, and mean other things. Means this deviation is to deviation covariance is my class. So let us see it mathematically, rather it is easy mathematically. rather going for definitions. WT, omega t is your vertical velocity at time t. T capital T is temperature, small t is time as I told earlier. T is your temperature at time t. Now, if you take this T in terms of average plus deviation, instantaneous value is always the average value plus the deviation. So if you resolve it this way, this T is your T bar, that is your average value, T dash is your instantaneous value. And similarly, in case of omega also, omega bar and omega dash. Now, if you multiply these two, rho Cp remaining constants, rho Cp you remove it because rho Cp are not varying. So you have got average component of omega, fluctuating component of omega, average component of T, and fluctuating component of T. So if you take the overall average of this, it comes. Now to get the overall average, you have to multiply these two and see how these terms there. See, now average upward wind speed, if you see, as I told earlier, average upward wind speed is 0 because if the average upward wind speed is something, then how the surface area is replaced? Surface cannot be empty. Surface cannot be empty. So there is upward and there is downward. So average of upward wind speed is 0. At the same thing for average of fluctuations. If you see the average, this is becoming 0 and this is also becoming 0. So only one thing is remaining, that is fluctuation into fluctuation. So that particular term is remaining. So my final form of equation is very simple: H into rho Cp into omega dash into T dash. Omega dash is fluctuation of wind speed, of upward wind speed. T dash is fluctuation of temperature. That's why I need so high speed measurement system, that to get this fluctuating component, I need this high measurement speed system. If you are not doing it as 20 hertz or 10 hertz, then the fluctuating component is not properly addressed. So you need to have this. This is your final part. Now this is computationally not very rigorous, but the thing is that because all the things are getting cancelled, this is computationally not very rigorous, but on measurement perspective, yes, omega dash and T dash are really difficult to measure because you are measuring it at high frequency. So the advantage, the same formula you can use for gas exchange, for any exchange processes, and this is the modern techniques nowadays. Based on this technique, all these Fox towers, there is a Foxnet all over world, and there is Asia Flux for Asian region, Carbo Euro Flux for European region, Ameriflux for American regions. So all are having flux components. Indo-flux for Indian flux towers are there. So this flux network is growing fast because of the climatic change. People are more concerned about the carbon dioxide exchange process, and this flux network works with this principle. This is the generalized principle. ISRO has number of flux towers nowadays at different stations, starting from Sundarbans to Barakpur. There is a flux tower. There are so many different places where there are flux towers. Now, EC technique is applied in general. This approach actually it's generally considered as this is the direct measurement of flux. So this one is a direct measurement approach, and others are indirectly measured like through resistance or through energy balance, but this one is directly measured. Now we understand there are three types of basic measurements of flux. One is covariance, the other is energy balance, the third one is aerodynamic, or you can put it in different ways. So EC technique works with a fast measurement system, And the limitation is availability of accurate and stable and durable sensors in this case. Now, sonicometer sometimes fails. I'm trying to discuss the limitations also. Sonicometer sometimes fails under heavy rain conditions. Then infrared gas analyzer requires frequent calibration. That is also an issue. And poor performance of sensors may be extreme temperature conditions because these sensors are all electronic sensors based on the electronic properties of the material sensing materials. They have certain measurement limitations. If you are going to extreme range, sensors may not give you accurate measurement. So these are the general limitations of EC techniques. However, in tropical conditions, a lot of EC towers are there, but there is an inherent problem in the tropical region because of the heavy rainfall. This you need regular maintenance of this tower preservation system. And aerodynamic approach, there are a lot of complexity with regards to stability of air. So under thermally stratified layer, the equation becomes very complex and the computation may lead to errors. So maybe when there is a very low wind speed, so that the eddies are not properly developed due to friction, eddies are most developed due to thermal reason. So in that case, maybe your system doesn't work well. This measurement may give you some false data. Bond ratio energy balance performs well under neutral condition. It doesn't justify thermally stratified layer because in a day you are getting thermally stratified layer at least 2 times. During late night or early morning, you are getting an immersion layer. During midday or 12 to 2 o'clock, at that time you are getting a very highly unstable layer. So these two conditions, they erode this bone ratio method sometimes then. However, when the net radiation and net radiation minus G is becoming zero somehow, so at that time bone ratio data is becomes indeterminate because denominator zero means you cannot define that, you cannot get the value of that ratio. So this is I'm almost at the end of my lecture, and let me sum up the things. So we have discussed about the concept of planetary boundary layer. We have discussed about the laminar versus turbulent flow Reynolds number. We have discussed about the logarithmic wind profile over the Earth's surface, and there are many related terms to it like frictional velocity, roughness length, zero plane displacement, eddy viscosity, aerodynamic resistance. So a lot of these things are related to this aerodynamic process logarithmic wind profile. Then we know what is Reynolds analogy and how this similarity hypothesis makes the flux transfer easy for us, get the flux computation process easy for us. Then in thermally stratified layer, the Richardson number and stability factor, aerodynamic flux in thermally stratified layer, bond ratio energy balance approach. I give you some understanding of bond ratio energy balance approach, and finally eddy covariance basic principles and limitations we discussed. So this is a summary of my work. Today's presentation, I mean to say, summary of my today's presentation. If anyone has any confusion, doubt, or any question, really ask me right now. Uh, I am ready to answer now, to discuss with you about your confusion or any